Hello and welcome to the next part of this lecture 1 on the big data foundation principles. So till up to the last point of the previous part, we were discussing about MapReduce and how it is an example of divide and conquer. In this lecture, we will start looking at Spark. Throughout the entire course, we will actually end up using Spark quite intensively, both having hands-on experience in Spark as well as reading up about the various features and capabilities of Spark become important objectives for this course. So I would suggest that you pay attention on what differentiates Spark fundamentally, which is what we will cover today, and this becomes the foundations for understanding the internals of Spark at a later point in time. So with that said, let's just start with saying that Spark itself is actually another example of MapReduce, rather divide and conquer, sorry. What I mean by that is, while divide and conquer is the foundational paradigm of how do you break a task into multiple simpler tasks which can be executed in parallel, MapReduce provided one version of it, one implementation of that paradigm. Spark provided another implementation of this same paradigm. So the similarities to MapReduce are more than just the fact that it's an implementation of divide and conquer. In particular, it also supports a variety of different types of programming languages. Scala, Java, Python were the primary interfaces when Spark started off, but then over a period of time, we've started to have so many different variations built by the community, built by the code developers themselves. And we've also started to have other components and open source projects which are translating their own respective constructs into Spark. So it becomes easier to use if you're familiar with certain types of simpler programming alternatives. The example being SQL, right? And one of the tools that we would take a look at a later point in time would be an SQL-based way of interacting with Spark as the backend. The other similarity is the fact that Spark is also built for big data, like MapReduce, so it scales to hundreds and thousands of CPUs, and it also has parallelization that's natively built in. But one key way in which the Spark designers distinguished its foundational architecture from MapReduce was the fact that Spark optimizes for memory in order to get speed. And this is as opposed to MapReduce, which are actually optimized for making progress in the face of failures. Now, this is not to say that Spark does not make progress in the face of failures, but it is the case that Spark became more constrained by how much memory was available in order to do more things faster, as opposed to being constrained by always failing components in a commodity cluster. Now, the reason for that evolution in Spark's foundational design is that since the time MapReduce was invented till the time that Spark came around and Spark became popular, there was actually this ever increasing set of improvements that have happened in terms of hardware, in terms of processing capabilities, in terms of resilience of components and hardware. Now that led up to a point that failures, while they were still much more common than, let's say, a supercomputer, you didn't have to optimize for as many failures occurring at the same point in time. Right? You didn't have as many failures occurring as when MapReduce was first implemented on a very basic x86 kind of an architecture. So what became more important though was the set of expectations that the broader industry had on big data processing frameworks. Specifically, people started to expect that apart from the ability to process large amounts of data, the speed of processing that data was important, right? People started to expect various types of processing workloads to be supported at the same point in time. And by that I mean not just long-running batch processing, but also the ability to do interactive queries, meaning I need to be able to do a query now and get an answer within 5 seconds. it doesn't matter the size of the data, right? So those kinds of interactive queries also had to be supported by the same backend framework. Then people started to express very complex workload patterns, and their expectation was the backend needed to automatically understand how to plan and execute that kind of a complex workload. Whereas what was happening with MapReduce was, because of the chaining of map and reduce operators with shuffle in between, the ability to optimize the plan to suit the execution that was needed for a complex workload was hampered because of that design. So as a result, the more complex a workload, the time it took to execute that workload versus the expectation that people had on the time it is supposed to take was massively different, right? And at times, for complex workloads, MapReduce just couldn't execute fast enough at all. Now, it's important to note, why was the expectation disproportionate to what was actually happening in MapReduce? One of the main reasons was that people were used to having operational experience with relational databases, which had the power to execute at scale. I'm talking the likes of Oracle, Teradata, IBM, and such, which were expensive alternatives that we briefly spoke about one of the earlier parts. But they also had very mature database optimizers, meaning you could give it a complex workload, and the database optimizer could construct a plan which took into account different aspects of the processing that was required and get it executed in good performance on a good set of hardware. That kind of expectation people started to have from big data, from Hadoop, because they were migrating from those kinds of infrastructure over to Hadoop. So as a result, the ability to basically get calculations done much faster than MapReduce became a need, and a lot of work happened at that time towards evolving different types of processing backends on big data. And Spark became a project that started off from academia, especially University of California at Berkeley. A bunch of grad students with a professor started to actually open source this project, and very quickly, within I think 18 to 24 months, there was widespread adoption for the kind of design that Spark fundamentally adopted, which was optimizing for memory. But yeah, if you look beyond that, what does Spark enable? It also enables automatic parallelization. Just like MapReduce, you don't have to worry about the size of the cluster or the size of the CPU, the memory, etc. It also enabled fault tolerance, meaning if one of the tasks were to fail because one of the machines was failed, then Spark would automatically spin up another task to get that job done. But the difference between MapReduce and this was that if there was work that was available in what's called as a RDD, I'll talk about that in a minute, then it could pick up from where it left off. But if the work was not available in an RDD, which means the work was transient and in memory, and if there was a failure of that machine, then the fault tolerance that was built in would spin up that same task in another machine on another copy of the data from the previous task outcome and execute from scratch, right? So sometimes this meant that Spark would take a bit longer for that task alone, but if you look at the broader global task, because Spark was optimized for speed, you would not really notice in practice, right? So yeah, fault tolerance is there. Obviously, Spark also catered to the ability to monitor and get status updates so that you know how much progress is being made, etc. That's also fundamental and critical to how Spark was designed. Now let's look at the core of the Spark design so that we understand and appreciate how it got its speed from. The fundamental unit of a Spark program is what's called as the Spark task, right? That executes in an executor. That Spark executor itself executes in what's called as a worker machine, and that worker machine could be just like the MapReduce machine, which is commodity hardware, and you could string together a bunch of these workers to create a cluster. And there is usually a Spark master. The Spark master is responsible for overall coordination of what needs to happen so that the work gets distributed across the executors and the workers. In practice, because each of the worker machines could be large in size, meaning anywhere from 16 GB of RAM onwards upwards to maybe even 124 GB, like 128 GB or 256 GB of RAM. And CPUs also could be anywhere from dual quad cores to hexa cores, quad hexa cores, etc. Right? So the workers were pretty powerful. So it made sense to actually have multiple executors within each worker. That way the unit of parallelism is one executor, not one worker. So the analogy is in MapReduce, the unit of parallelism is one map task or one reduce task. So here, the way that the tasks were formed is where the meat of the difference is, right? The tasks are themselves embarrassingly parallel, and the tasks, when they need to execute in such a way that they need to exchange data, there is a notion of a shuffle that is also available. But what is the task and how does it get created or planned with respect to the global problem statement that you're trying to solve for is where the difference really comes from. So the fundamental unit of the Spark execution is the ability to do lots of different types of standard transformations, which are all clubbed together as ready-made functions, and those functions are organized in a tree of operations, which is called as the directed acyclic graph, or DAG in short. An acyclic graph is actually a tree, effectively, right? The directed acyclic graph just talks about the fact that the tree of operations needs to have an order through which those operations need to be performed in order to get the right result, right? So each operation here could be a simple task which just looks at rows of data individually, or could be a task which looks at a row of rows of data collectively. What I mean by individually is that every row of data can be processed independent of any other row. So in that sense, it's very similar to the kind of logic that you would put in a map task. And what I mean by collectively is a bunch of rows needed to be looked at together based on some kind of a property which is common. So one example would be a key-based aggregate, where the key is a column that's there in all the rows. So the example in the world of MapReduce would be a group by, which is executing as part of a reduce function, right? So here in Spark, both map and reduce are expressed as transformations, and those transformations are ordered in a DAG. Now, every now and then, you will also do actions on top of those set of transformations. An action is defined as something that produces an externally visible output. Could be that the externally visible output is in the form of writing to a file, right? Or it could be that the externally visible output is in the form of collecting data to print to the console, right? So that you want to take a look at the data or something like that, right? Or you want to debug further. Or it could be that it's producing files of data as output on a storage device. Doesn't matter, right? Anything which is producing output for consumption beyond the Spark application, beyond the Spark program. So those are called actions. The reason actions are segregated from transformations is that actions have side effects, right? Actions are side effects, which means that I cannot always redo an action without having some other consequences which are potentially changing the nature of those side effects. What I mean by that is, if I execute an action, let's say the action is writing data to a file, then because the program has failed, if I have to rerun the program and therefore I have to redo that action, I will not have the guarantee that I'll not create corrupted data, because I could create another copy of the file in the same storage area, and somebody who takes a look at that storage area could find two files, one corresponding to the previous attempt at writing that file, one corresponding to the latest attempt. And the previous attempt could have failed or could have succeeded, I don't know. The current attempt could have failed or succeeded. But then in aggregate, I have basically data in that file which is not reliable, unless I design for it very, very carefully. That's why, because there is a need for designing carefully for those kinds of actions, for those kinds of operations which produce a side effect, Spark designers distinguish actions from transformations. Whereas in the world of transformations, right, I could do a bunch of different transformations. I could chain a bunch of transformations together. Doesn't matter because they don't have side effects. It's up to the Spark program to figure out how to order them, how to get the best out of the performance of the resources. So that's why there's a distinction. Now, a specific Spark program is modeled as a directed acyclic graph, where the DAG stops is at the point of an action, right? When the action is performed, there is a logical stop to the DAG because it creates a side effect. You could continue to produce other transformations after those actions are performed, which necessitates what's called as a different stage in the DAG, but the fact remains that logically one stage is completed the moment a specific action is performed. The practical way in which Spark executes its task is every stage of computation, it tries to group all of that together so that it just runs through it in one continuous operation. And in doing so, it knows that the output of the next operation that's part of the same stage is available in memory based on the computation, based on the current task that's executing. So that's what these arrows indicate, right? So this particular task P executes on one machine, rather one block or one executor, and then it finishes, and its output needs to be distributed amongst 3 different executors. Could be residing on the same machine or different machine, doesn't matter. But then that job of making the data distributed directly can go from memory to memory. Doesn't have to go through disk at all, right? Memory to network to memory. And it knows that it can continue executing that stage because there is no action involved that logically stops that stage. So on the left you see an example of a Spark program. What you see here is a functional programming syntax. You'll get used to it when you start working with PySpark, but for those who are used to Python itself, you could write perfectly valid procedural programs using Python, but Python is also very good at exposing a functional programming interface. With functional programming, what you get access to is the ability to reason about objects and what they produce as inputs and what they produce as outputs, what they need as inputs and what they produce as outputs. And you could look at chaining all of them using a notation like this, which makes it extremely easy for you to reason about what is happening where, right? So this kind of a chain, I go through this specific Spark program, which reads data from a table. The table happens to be stored in a NoSQL database called as Cassandra. We will take a look at what NoSQL means at a later point in time. And then once it reads data from this table, then it does a map operation. Notice that this map operation in Spark is different from the general purpose map paradigm or map type of function that's there in MapReduce. Here, map refers to any activity, rather any operation which allows you to map one row of data to another row of data. Effectively, it's a scalar transformation function, right? It just converts one set of columns to another set of columns for a row, and you could do it for multiple rows. That's how the map function is defined. Filter, like you can imagine, is filtering certain data out. Key by is basically suggesting that I need to collect rows based on a specific value of a key. Reduce by is basically clubbing a bunch of these rows into a specific, rather clubbing a bunch of rows based on a common key value and then applying some kind of a function. Could be an aggregate function as an example. And then cache is where it tells the Spark executor to keep a copy of the output that's produced by the reduce by key into memory so that I can come back and access it at a later point in time. So as you can imagine, the cache is actually going to be an action, right? That makes all of these operations as part of one stage in terms of execution. Okay, now at each point in this particular Spark DAG, right, you could actually look at the output of each of this operation as logically corresponding to a particular unit of data which is necessary for the next program to actually pick up and execute. Now what happens if one of these programs fail? and what happens to the next program that needs to execute. Then the next program will have to wait for this previous program to begin again, right? And then produce that same output. Now, if this program has produced the output, but the next program has failed in the middle of the execution, does that mean I have to go back to that first program and start all over again? The answer is no. The reason being, Spark actually has natively constructed in-between storage systems for these datasets, which allow it to pick up from points of failure by just executing the next next task, and then picking up the output from the previous task from well-known storage areas. Those objects where these datasets are temporarily stored are called as RDDs, or resilient distributed datasets. Resilient corresponds to the fact that it doesn't matter if you have failures. The moment a specific operation is completed, then the unit of data that it produces as an output is available even if that subsequent consuming program fails, right? Even if this program were to fail, that resilient distributed data is available so that you can pick up from where you left off, or you can start all over again with the next task, and you know for a fact that the data from the previous operation is available for you. It's distributed in the sense that at every point when a particular task or set of tasks is done, which logically represent an operation like a map function, then all the output of the distributed computation of that map function across all the distributed sets of data, they're all available as resilient distributed data sets. That's the notion of distributed that it's referred to here. And data set, as you can imagine, is just the data, right? So, as and when a specific operation is done in parallel by multiple executors and it produces the output successfully, then an RDD is created so that the next operation can continue from where it continue from that output. And if the next operation were to fail, it knows where to look for the RDD corresponding to the output of the previous step. So that's how these RDDs are chained together. You can imagine almost as though the DAGs themselves correspond to the RDD tree, right? There is a one-to-one equivalence between the two. Okay, the entire program, the entire program of operations that corresponds to a DAG is encapsulated within what's called as the Spark application. And when a Spark application executes, it needs to ask for itself resources in order to execute. And those resources are all encapsulated within a variable which is called as the Spark context. So think of it as the Python environment. That's the analogy here. So the Spark context encapsulates the entire application, and whatever needs to happen with respect to the memory utilization, the CPU utilization, the task execution of the executors, etc., all of them happen on behalf of the Spark context. So that's why you see this variable SC, which is being referred to here. This snippet of code is shown here as a Scala snippet, but obviously there are PySpark snippets as well that's available. Spark also has its own manager for managing resources, which is called the Spark Cluster Manager. But in reality, Spark actually has bindings with other cluster managers which are popular. Yarn is one such example. Yarn stands for yet another resource negotiator. Yarn is very popular in the world of Hadoop, but since then there have been many variations of Yarn or Yarn itself that has been adopted by the cloud vendors. So in most practical cases, you'll see that Yarn and Spark are the typical combinations when running Spark at large scale, even without Hadoop being involved in the picture. Alright, so let's move to the next foundational topic, which is important to understand. We spoke about how MapReduce was optimized for making progress in the face of failures. And the way it made that progress was to ensure that the outcome of every single step is written to files on disk such that I have access to those files of data, even if there are failures of downstream processing. That ended up creating a pretty slow execution in practice compared to the Spark way of doing things, which also tried to optimize, also tried to take care of failures, but it optimized for speed as opposed to optimize for making progress and failures. So what Spark did effectively was make use of memory a lot more. One of the ways in which Spark uses memory very well is by optimizing the footprint on memory. And in order to optimize footprint on memory, it's important to understand what are ways in which you can solve the problem that you have at hand, which uses less memory than what you would otherwise use. Towards this, it's important to understand this concept of sorting and hashing. And in fact, the foundational principle is that whatever you could do with sorting, you could actually do with hashing that same data. That's what is referred to as duality. Sorting corresponds to being able to group a bunch of data together such that it's ordered based on some attribute that you're interested in or a set of attributes. Hashing corresponds to reading data such that you read a bunch of data and index it such that data that has the same value for a set of attributes occur together or get indexed together. So the duality of sorting and hashing was first talked about in a landmark database paper back in 1993. But since then, that paper has actually been such a seminal, has had such a seminal influence on the world of database research and as well as the world of distributed systems that a lot of design principles around how Spark is used and how the algorithms within Spark are designed picks up from the decades of database research that followed rather from this specific paper. So whatever you could do with sorting, you could do with hashing, which means that there are some approaches which are potentially faster because you adopt a hashing based mechanism as opposed to a sorting based mechanism. Why would that be the case? It's important to understand for this the algorithmic complexity of sort based algorithms and hash based algorithms. So what algorithmic complexity refers to is what is the theoretical complexity of executing an algorithm when the algorithm operates at scale, right, on a piece of data. For a specific sorting function, let's say for instance the quick sort, right, which is the most popular method of sorting data. The algorithmic complexity is what's called as, what's referred to as big O notation n log n, where n is the number of rows of data that needs to be sorted. Now the big O notation is what's called as the asymptotic complexity, which means in the worst case, as the quick sort executes, you would need n log n computations in order to sort n amount of data, right? Now that algorithmic complexity expressed in that n log n fashion with big O notation is only applicable at small scale of data. The reason being, you're simplifying the assumptions of how long it takes to compute the comparison between two rows of data, which is what Quicksort does, right? Computes two rows and decides whether one is small, one is larger. That computation is equal in cost. The comparison is equal in cost for reading both of those data sets, only if those data sets are available to be read from, read by the CPU in the same order of magnitude of time. Now that's obviously true as an assumption only if that data set was in memory, right, or that data set is available in the cache line of the CPU. What happens if the data is large in size, right, and as a result the two rows that you're comparing have to be read from disk? In which case, like we looked at in one of the previous videos, the time it takes to read data from disk is going to be at the minimum, right, microseconds, right, hundreds of microseconds, if not even milliseconds. Whereas the speed at which the CPU executes is also already known to be at a latency of nanoseconds. So the comparison between two rows of data in memory versus two rows of data from disk is going to be orders of magnitude different. So it no longer makes sense to say the quicksort algorithm executes at order n log n computations or order n log n time if those operations of comparison between rows of that n set of data are not comparable with each other, right? Because some of them are in disk, some of them are in memory. So what you do then is, you start to look at algorithms with scale, right? Which scale with data set. Quicksort does not. Quicksort assumes that all the data is available in memory. But there are algorithms like merge sort, which basically operate at groups of data together. And merge sort allows you to scale by spilling intermediate data sets onto disk. And that is possible by, that it does by breaking down the data set into smaller chunks, and then it sorts each of those chunks by doing effectively quicksort, right? And within the chunk, as soon as the quicksort algorithm is done, then you have a fully sorted data in memory, then you write that to disk, pick up the next chunk, etc. Once all the chunks are done, then you look at all the chunks individually, one by one, pairs of chunks at a time, one by one, each pair at a time, and pick up the top rows of each pair, compare the two, and so on and so forth, and you move the iterators over, right? In a sense, that's the quick view of merge sort. I encourage you to read about it online, but merge sort is meant for large scale, right, of the data. So what I just spoke about as the implementation of merge sort is essentially a divide and conquer example, right? And that's easily implemented in a programming paradigm like in a programming framework like Spark or MapReduce using the shuffle function. So that's in terms of sorting, right? Now, if you had to think in terms of hash algorithms, the foundational unit of a hash algorithm is what's called as a hash table. Effectively, what hash tables do is what we will look at as part of the next video.